Today we're presented with the following problem, and that's prove that for all values of n to the 7 minus n, prove that for all values n to the 7 minus n is divisible by 42. Now for 42, well, to say a number is divisible by 42, it must be divisible by 2, 3, and 7, as this is the this is 2 times 3 times 7 is the product of prime factors for 42. Now how do we show this? Well, let's take n to the 7 minus n and see what we can do with it. So we can first start off by factoring out n. Now we've got a difference of 2 squares, so we've got n cubed plus 1, n cubed minus 1. Now we can use a little trick that we know, which is b to the n minus a to the n equals b minus a, b to the n minus 1 plus b to the n minus 2, a to the 1 plus so on and so forth up until b to the, well, a to the n minus 2 is b to the 1 plus a to the n minus 1. So we can use this formula to evaluate n cubed minus 1. So we've got n cubed plus 1. We've got b minus a, so where b is, so we can see minus 1 is minus 1 cubed. So b minus a is n minus 1. Then b to the n minus 1 is n squared plus b to the n minus 2 times a. So that's n multiplied by minus 1, well, no, not minus 1, just 1, so that's n. And then we've got the last term, a to the n minus 1, which is 1 to the 3 minus 1, which is 1 squared, which is just 1. Now, you think it could be done, but we can write n cubed plus 1 as n cubed minus 1 cubed. Evaluate this, we get n cubed minus 1, which is just n cubed plus 1. So we can rewrite this as n plus 1, since we've got n minus 1, n squared, then we've got b to the n minus 2, so that's here n minus 1 times minus 1, which is minus n, and plus 1, n minus 1, n squared plus n plus 1. Right, we can't simplify n squared minus n plus 1 or n squared plus n plus 1 any further. So now we have to show that this expression is divisible by 2, 3, 7. For 2, well, we can just say that we've got the product of 2 consecutive integers, n plus 1. And we know that in this product we must have one even and one odd, and anything times an even will just spit out an even, and all evens are a multiple of 2. So we can say for 2 we have n times n plus 1, which is even, therefore it's 2. Now for 3, well, we've got n minus 1, n times n plus 1, which is a product of 3 consecutive integers. And in any set of 3 consecutive integers, we always have a multiple of 3. Therefore, this is a multiple of 3. We can take this, 7. Now for 7, this is a bit more tricky. we can't go about it a simple way and say that this expression is divisible by 7 using any of the methods we use for 2 and 3. So we have to think outside the box. I'd use a bit of modular arithmetic and say that this expression, mod 7, must equal 0. And we have a few different set of values for n that n can hold when we're dealing with mod 7. We have 7k plus 0, we've got 7k plus 1, 7k plus 2, 7k plus 3, 7k plus 4, up until 6. Because when we have 7k plus 7, we take the mod of this, 7k plus 7 is congruent to 7k plus 0 mod 7. So if you take the mod of all of these expressions, we get 1, 2, 3, 4, 5, 6, and again 0. So if we can show for values 0 to 6, when these numbers are n, that the mod of our expression is 0, then we can say that this whole expression is divisible by 7. So let's make a grid to show this. So we'll have all our terms as the columns. And then we've got all products. So we've got n, we've got n plus 1, n minus 1, and then we've got our quadratic terms, which are n squared plus n plus 1, and the other one was n squared minus n plus 1. Right, and we're doing mod 7 and for all these inputs. So we've got n as 0. For the term n, we have 0, 1, 2, 3, 4, 5, 6. n minus 1, we've got 0, minus 1, which is minus 1, which is congruent to 6. 1 minus 1 is 0, 1, 2, 3, 4, 5. n plus 1, we've got 1, 2, 3, 4, 5, 6, and we've got 7, which is congruent to 0 when we deal with mod 7. Now we've got our quadratics. We've got 0 squared plus 0 plus 1, which is 1, 1 plus 1 plus 1, which is 3, 2 squared, 4 plus 2 plus 1 is 7, so that's just 0, 3 squared 9, plus 3 is 12, plus 1 is 13, 13 mod 7 is 6. And then we've got 4 squared plus 4 plus 1, which is 21, which is congruent to 0. 25 plus 5 plus 1 is 31, which is congruent to 3, mod 7. 6 squared plus 6 plus 1, 43, and then 1. And then n squared minus n plus 1, we've got 0 minus 0 plus 1, 1 minus 1 plus 1 is 1, 2 squared is 4 minus 2, 2 plus 1 is 3, 3 squared is 9 minus 3 plus 1, which is 7, which is congruent to 0. 4 squared minus 4, which is 12, plus 1 is 13, which is congruent to 6. We've got 5 squared, which is 25, minus 5 is 20, plus 1 is 0. 6 squared, 36, minus 6, plus 1 is 31. 31 is congruent to 3. Right, now we said that we need to show for each value of n that the expression is mod 7. That the expression mod 7 equals 0. The way we show this is that if one of our terms is equal to 0, then the rest of the expression equals 0. So we've got a 0 for when n is 0, 0 for n is 1, 0 when n is 2, when n is 3, we've also got another 0, another 0, another 0, another 0. So we've shown for all values of n, mod 7 equals 0, which means we can tick that our expression is divisible by 7, meaning, well, since it's divisible by 2, 3 and 7, it's divisible by 42. Now that's all for this number theory question. I hope you enjoyed. See you the next slide.